Hey folks, in this video we're going to learn how to use the Spartan Student version to build molecules and do quantum mechanical calculations to determine their three-dimensional structure, determine properties such as the dipole moment, and to actually generate the infrared spectrum. So let's start with the simple molecule. So what we're going to do is we're going to go through and select a new molecule. Now, the version of Student Spartan that you open may have these icons at the top. It may be a little bit different than the version I have here, but one can always find within the file menu, for example, a new build, for example, to build a new molecule. We can alternatively click this icon here. And then what comes up is a palette of, in this case, the organic palette. And we're going to just focus on the organic palette in these exercises. The inorganic palette, actually, if we click on that, you'll find that you can actually bring up the entire periodic table and select a particular element from that. But we're just going to select the organic palette. And what you see are different types of bonds to basic atoms that are common in organic chemistry. So let's just start building some molecules. So let's just start with a simple molecule like O2, oxygen. Now, if we do the Lewis structure for O2, and if you don't remember how to do that, go back and look at your class notes. But what we're going to do is we're going to select O2, which has a double bond, and I'm going to select this oxygen right here, and I'm going to double click within the window, and now I'll see an oxygen with a double bond. Now remember, a double bond means that there are 4 shared electrons, 2 pairs of shared electrons in this molecule. And then to attach the other oxygen for O2, I'm just going to continue. Notice that this is still highlighted, so when I click, it's going to do that. I'm going to click on the bond here so that we can see that. I can make this bigger by using my little scroll button on my mouse. I can rotate the molecule like so by just left clicking and rotating. Okay, so this is a basic oxygen molecule. Nothing special here, but let's go ahead and do a simple calculation on this molecule just to familiarize ourselves with what we're going to be doing in this exercise. All right, so we're going to go up here to Setup. Going to choose Calculations. And then we come up with a bunch of different possibilities here for this. I'm going to pause here for a second because I'm about to sneeze. Okay, I'm back. And you'll see what comes up is a window here with several options. Equilibrium geometry, and that's generally what we want. And what that means is it's going to do a calculation to find the most stable geometry of atoms in this molecule. So we're going to do that. Now, the kind of calculation we're going to do is what's called a semi-empirical calculation. And we don't need to worry about the details of that, but we're going to use PM3. And that's just a data set, basis set of mathematical functions that are going to be used to do the calculation. All right, so we see equilibrium geometry, PM3. And now what I'm also going to do is I'm going to select IR, because what I want to do is I actually want to calculate the infrared spectrum, which means the vibrations in the molecule. This will give us vibrations in the molecule, and we'll talk a little bit more about that. And again, you can review class videos to actually get more information about vibrational modes in molecules. Right? And then I'm just going to go ahead and I'm going to submit. Now, the time it takes to do the calculation, now it's going to ask me to enter a name, and I'm just going to leave it. It will sometimes suggest a name, and if you're okay with that, you can just leave it that way. I'm going to leave it that way. And it starts the calculation. Depending on the size of the molecule, it may take a little bit of time to do it. You can see in this case, it's a small molecule. It's relatively easy. It's already finished the calculation, so it's okay. All right, so you may have noticed when I clicked that the atoms got closer together, and so the calculation indicated that does a calculation to determine what's called the bond length, and that's the distance between the two atoms. And we can actually get information about the bond length. If you click on the bond, you'll see down here on the right corner, it shows 1.17 angstroms. An angstrom is 10 to the minus 10 meters. So 1.17 times 10 to the minus 10 meters, or if you want, 0.117 nanometers is the distance, calculated distance between the atoms. Okay. Now, among the things that we're going to try to determine here is to go ahead and look at things called the dipole moment. So we're going to go up here to display, and we're going to select properties. All right. Select properties, and I'm going to unclick the bond here so we get the properties of the entire molecule. All right. And so it gives us information like energies and things we're not going to be terribly concerned about, again, in this particular class. But here we go. So one of the things that we're interested in is what's called the dipole moment. And the dipole moment is a measure of the polarity of the molecule and the charge distribution in the molecule. And again, perhaps review some of your class notes with regard to this. But because we have two different oxygen atoms, again, you can think of it like a tug of war. We have two oxygen atoms here in this molecule, and they're both attracting electrons. They want to pull electrons toward them, but because they're the same atom, because this is a symmetrical molecule, they both have an equal pull. Nobody wins the tug of war. It's a draw. So there is an even distribution of electrons throughout the molecule, and that means that it's a nonpolar molecule. The dipole moment is 0, all right, which is a reflection of the fact that it's a nonpolar molecule. So that's the basic calculation. Now, let's take a look at the infrared spectrum. And again, there are a couple of different ways you can do that. You might have an icon at the top of your page to select that, or we can go to display, and we can go down here to spectra. We're going to click on that. All right. And you can actually make this a free-floating box if you want. That makes the molecule, notice it made the molecule look bigger. So I'm going to add spectrum here. And because I selected infrared, all right, I can click on this. Well, what we know is that if we've got a nonpolar molecule, all right, and particularly a diatomic molecule, when that molecule is going through a vibration, and let's pick out the vibration and show what it's doing. Okay. Then go through, and I'm going to click on, I select this little spreadsheet box here, okay, and I'm going to click on this guy, and that shows basically the molecule stretching and contracting, stretching and contracting. So one thing to note is that molecules are vibrating all the time. The bonds are stretching and contracting. In other molecules, you notice the bonds, we'll see that the bonds are breathing or bending, and that's called a vibration, okay? And that vibration is an indication, again, that vibration shows that as it's stretching, the dipole moment doesn't change during that vibration, and if the dipole moment doesn't change, it doesn't absorb infrared radiation, which is actually because O2 represents 20% of the gas in our atmosphere. If it did absorb infrared radiation, we'd be in trouble because infrared radiation is emitted by the Earth. Infrared radiation is coming in from the sun. The atmosphere would be absorbing infrared radiation, and we really would be an overheated planet if that was the case. But it doesn't absorb infrared radiation, so it's a good thing. And that we don't have, it doesn't absorb that, so therefore it's not actually contributing to the heating of the atmosphere. So that's an IR spectrum, and that's the vibration. It shows the intensity here at 0, and that again, there's little tiny things here in the infrared spectrum, but we will note that essentially it doesn't absorb infrared radiation. All right, so let's unclick that, okay, and I'm going to close this out. Let's build another molecule, all right? So what I'm going to do is I'm going to again go to a new build, and you'll notice when I do that, actually, we haven't lost the oxygen. It's still here, but we have a tab, 2 tabs, all right? So I've got this new build. I've got a tab here so that the O2 is still there. So let's build a molecule like ammonia. Okay, so ammonia is NH3. So I'm going to click here on the nitrogen. It's got 3 bonds to it, so I'm just going to click on this. I'm going to double click in my window. All right. And now, okay, I'd add. Now, one of the things about Spartan is if you don't add the atoms, I'm going to go ahead and do that. But if we don't add atoms to the bonds, it's going to assume that hydrogen is what you want. I'm going to go ahead and select hydrogen here and then just click on the bonds at the end. There we have it. So there's our ammonia molecule. Now I'm going to do the same calculation. So I'm going to go up here to Setup, select Calculations, Equilibrium Geometry, PM3, click on the IR box, and Submit. And it's going to give us a name. It knows that it's ammonia. So we're going to go ahead and save it that way. All right, finished the calculation already. All right, so let's do the same thing we did before. We're going to Display. We're going to display Properties. And now you can see it has a dipole moment. And let me drag. I'm going to right-click on this and drag it over. So if you right-click and grab the molecule, you can actually drag it. All right, so here it is. It has a non-zero dipole moment. That means it's a polar molecule, which you could probably suspect it would be polar because what we can see here is that we've got kind of an asymmetrical molecule in the sense we've got nitrogen and 3 hydrogens below it. Now, if it was flat, it would be, and we'll look at an example of some flat molecules, it would be nonpolar. But this is because the nitrogen, it's not in the same plane. This is a polar molecule with a non-zero dipole moment. And if we actually displayed the dipole moment by clicking on this little box here, it shows an arrow, which the way the arrows are down here, a dipole moment, remember, represents an asymmetrical charge distribution within the molecule. So that means that we've got one side of the molecule that's going to have a slight positive charge and the other side of the molecule which is going to have a negative charge. And so nitrogen is very electronegative. It's pulling electrons toward it. And so we've got a negative charge up here toward the nitrogen, the electron distribution within the molecule such that it's negative up toward the nitrogen and positive down here in the hydrogens. All right, so it does have a dipole moment. All right, it is a polar molecule. And that again is because it's got this asymmetrical structure. Okay, all right, so now let's go ahead. I'm going to click out of this and let's go ahead and do the spectrum again. Display spectra. I'm going to add. Right, now you see a bunch more peaks here. All right, so let's take a look at the vibrational mode here. And you'll notice that it's got 1, 2, 3, 4, 5, 6. Now, these units are inverse centimeters. They're called wave numbers, 1403. So I've got 6 vibrational modes. The most intense is this one at 1403. All right, so let's go ahead, and again, I'm going to move this, right-click and move this up here like so. Okay, and select them. The most intense is 1403, and so you can see here's the peak over here. All right, and you see what it's doing. It's kind of flapping its wings. All right, that's a vibrational mode, and that very strongly absorbs infrared radiation. There's one at 1,759 inverse centimeters. All right, and you see how they're kind of waving is how we might describe that. All right, go ahead and click on these and see what they look like. 60 and 3,661, where it's really just kind of stretching very strongly. And that one's the weakest, the least intense of the bunch. So that would be that situation there. So let's stop that. Out of this. Let's build one more molecule. So let's build a molecule which has carbon atom in the center and 4 bonds to it. Okay. Let's go ahead and let's actually make methanol, which is a molecule we talked about earlier. So methanol has a structure with an alcohol, and alcohols have an oxygen and a hydrogen, right? So that makes it an alcohol. Okay. And now the rest of them are hydrogen, and I can go ahead and click on those to generate that molecule. All right, so this is methanol. So we'll go ahead and go to calculations, equilibrium geometry, PM3, click on the IR box, submit. It knows it's methanol. Save, start the calculation. Done. All right, so here's our molecule. And again, what we can do is, as I mentioned earlier, we can do things like clicking on a bond and we get the bond length. You notice that the bond length here is longer than the oxygen-oxygen bond length that we had. And that's due to the fact, largely due to the fact that the O2 bond length that we had in this molecule, 1.170, was a double bond. And double bonds are stronger bonds, and that also makes them shorter bonds. So it's 1.17 angstroms, whereas the carbon-oxygen bond is a single bond. And if you go back again to Lewis structures, it's a single bond, and that's going to be not as strong, and it's going to be longer. Single bonds are longer than double bonds. All right. And so here is that situation. We can also do things like measure something called the bond angle. So if you can imagine this, let's go ahead and measure the angle. And I'm going to select 3 atoms here. All right. So it's going to measure this angle right here as 107.45 degrees. All right. So this gives us information about the geometry, again, the geometry of the molecule, which is very influential determination of properties as such. So, all right. So there is our methanol molecule. And again, let's go ahead. Do you think it's got a dipole moment? Is it symmetrical? Well, it's not, all right, because if I had a hydrogen here instead of an oxygen, if it was just CH4, which is methane, everything would be symmetrically disposed about that carbon atom, all right, and that would give it a 0 dipole moment. But it's not symmetrical because I've got this oxygen here, which is a very electronegative atom, and it is really trying to pull electrons toward it. It is the second most electronegative atom in the periodic table, fluorine being the most electronegative. So it's really, electronegativity means it's pulling electrons toward it. So if we look at the dipole moment, it's 1.49. It does have a dipole moment. And we'll see if we display the vector here. This shows the negative end of the molecule is up here, close to the oxygen because it's pulling electrons toward it. The positive end is between the hydrogens. Okay? And so there is my molecule, my 3-dimensional structure, all right, with the dipole moment. So let's take a look at our IR spectrum. This time I'm just going to click on the icon, and we're going to add IR to this. Right, and here we see several bonds several peaks here. All right, so let's click on the modes. Now, you see there are a lot more vibrations. And the general rule of thumb is that there are 3n, for a nonlinear molecule, there are 3n minus 6 vibrations, where n is the number of atoms. All right, so in methanol, I've got 1, 2, 3, 4, 5, 6 atoms. So 3 times 6 is 18. And if I subtract 6 from that, that gives me 12 vibrations, different types of vibrations in the molecule. All right, the most intense vibration is here at 1408, has an intensity of 1. So if we click on that, this around a little bit, you can see we got this kind of, the hydrogens are going up and down, and the carbon-oxygen bond is also going up and down. And that's what that vibration looks like. That's the most intense vibration in that particular molecule. All right, and then we can click on others. All right, others are not nearly as intense. Let's get a 992 here. All right, at 0.21 intensity. And again, you can see the vibrations there and how the atoms are moving around as the molecule vibrates. And this one absorbs, again, these are absorbing infrared radiation. Some of them are really, really weak that hardly absorb any infrared radiation at all. For example, this one is a very weak vibration. All right, it's almost kind of it's the carbon-hydrogen bonds are stretching and contracting in that particular vibration. So let me click on that because it was below the screen. But 3068 is the weaker vibration. Okay, and then 3141 is even weaker. Now again, it's carbon hydrogens moving around. So that's basically it. This is how we're going to use Student Spartan to construct a three-dimensional perspective on these molecules to figure out the molecules are polar or nonpolar, and to look at their infrared spectrum. Why are we concerned about the infrared spectrum? Well, the thing that we're going to focus on at least is the environmental impact. Because if molecules absorb infrared radiation, and if they're in the atmosphere absorbing infrared radiation, they can contribute to global warming and climate change. And the stronger they absorb infrared radiation, the more they're going to contribute to the problem, right? And it's also important to note which of the types of vibrations are absorbing it. So this concludes our brief introductory discussion of how to use Student Spartan to construct molecules and learn about some basic properties. If you're interested in more, we can go into more depth here and actually generate videos which explore some of the other aspects of this program. If you have any questions, let me know.